So key thing to note, a function is a relation, but not every relation is a function. And when we say function, we typically mention an entire continuous graph. But for the sake of it, here, in terms of a relation, a function is simply a set of ordered paths. And x comma y is what we mean by a set of ordered paths. The reason why we call it ordered, because the x-axis and the y-axis on the number plane, they have a natural ordering to it. So any path that you pick on that plane is going to be ordered. So let's say we've got a bunch of points and we'd like to find the domain and the range. From last time, what is the domain?
All the x values?
All the x values. The range would be all y values. So as a set, I can write all the x values. It is an ordered pair, and we always write it as x comma y. So 1, 2, 3, 4. Range is the set of all y values. And what are the y values? 2, 4, 9, and 16. I'm just splitting them up as x and y values. So we can define if, we can determine if a relation is a function or not by doing what we call a vertical line test. Of course, vertical line test would only work if you have a nice little curve. But what if you simply have a relation same problem, and the second point I changed it to 1 comma minus 2 from 2 comma 4. If you drew it the way we usually do domain, range, the numbers, the x values, 1, 2, and 3. Y values, 2, negative 2, 4, and 9. Good. And we can connect with lines like we did last time. So you can say that one x value is mapped to multiple y values. It doesn't have to be just 2. It could be infinitely many, but 2 is sufficient. So if you have one value mapped to two y values, then we don't have a function. But why do we call it a vertical line test? Any thoughts? Why do we call it a vertical line test? Do we understand this part? For one x value, you cannot have two y values, in which case the relation is not a function. So here we don't have a function. Have we heard of a vertical line test before? Does anything come to mind? Yes.
So why isn't it a function again?
One x value has two y values.
Oh.
One will have two. That's the first point. The next point is 1 and minus 2. 2, comma 4 and 3, comma 9, somewhere over here. Good. If I drew a vertical line through this point, at how many points will it touch that one single point? Kind of weird way of putting it. If I drew a vertical line here, x is equal to 3, will it touch that point? Yeah. Yes. Will it touch any other point?
No.
No, there is only one. So only 1 point. How about that one?
1 point.
If I do a vertical line, it is going to touch exactly 1 point. How about that one?
2.
2 points. So when we draw a vertical line through a function, which in this case it's not, hypothetically, when I draw a line, it has to touch exactly at 1 point in the range. So simply put, a single x value cannot have two y values. It has to make up its mind. Good. So it can either be 2 or -2, but not both. So in that case, the relation is not a function. So what is the domain?
0, 5, 7, 5.
0, 5, 7. We don't have to write 5 twice, right? 0, 5, and 7. What about the range? 0, 13, 11, and 9.
That's not 9.
It's a 0.
I mean, oh, I'm gonna.
So 0 is connected to 0. So 1 point in y is connected to 1 in x. So domain range. So likewise, 7 is connected to 11. Very creative. What about 5? 5 is connected to 13 as well as 9. You know, think of that V shape. What? Yes, to that.
It's not a 9, it's a 0.
It's a 0.
Oh, that's a 0?
Yeah.
Oh, well.
So far, it's a 0.
It's okay.
It's a 0.
I guess I'm drawing blind. 2 zeros touching it. Okay. So is it still a function? No, because one value in x is connected to 2 different values in y, so this cannot be a function. Is it a relation? Yes. Good. So it's a relation, but not a function. If you can't visualize this right away, you can use a graph. Zero, we have 0. 5, wow, 13. 0, 13 somewhere up there. And 7 connected to 11, I'll just put somewhere up there. But you can see that those 2 points are in a vertical or on a vertical line if you draw one. So that particular relation cannot be a function or is not a function. Yes. Any set of points is a relation. So, come again?
The one that we just got with the relation.
Yes. A relation is a set of ordered paths. It doesn't necessarily have to be numbers, x, y paths. It could also be like the example that we did last time, where I had where people were from, Lehigh Acres, Fort Myers, Cape, and then the ice cream flavors that they love, right? So I connected the place to the flavor. That is also a relation. Does that make sense? I believe they have an example of that sort in the textbook. Any questions here? No? Okay. I have New York and Chicago, and the rest are heights. 1776, 1451, 1396, 1389, 1250, and 1200. So New York here is mapped to 1776. 1396, 1250, and 1200. And Chicago is mapped to the other two. So things are related. I've related the tallest building in a city with the height, but does it form a function? It doesn't. So a function pretty much should have one value for x, and there should be one resulting y value. So the domain here is just New York and Chicago. The range those numbers, and clearly it is not a function. By all means, we don't care to write relations as functions or not unless there are numbers. Functions always deal with numbers, at least in mathematics. Okay. So we saw tables for relations, which could be a function or it couldn't be a function. Let's take this example, 1, 2, 3, 4, and 5. So the metric conversion, we have miles to
Kilometers.
kilometers, so. Just multiply those by 2 and 3 and so forth. Do you believe that this is a function?
Yes.
Yes. So how would we express it if this is a function? Can you give me a formula?
F of X.
F of x. Okay, so what should the output be?
The miles multiplied
Okay. The miles multiplied would
by
give you
kilometers.
miles multiplied by kilometers. Okay. Anything else? So think of it this way. I have a box. That's the metric conversion box. Miles goes in, what should come up? Kilometers. Okay, so that box right there is the function, right? Clearly, we have a relation, but is this relation a function? Yes. Do we have one y value for an individual x value?
Yes.
Yes. I don't have an x value that maps to 2 y values. So clearly this is a function. So it's a relation as well as a function. It will pass the vertical line test. But now I want to know if there is a different way to write this function. So we have seen a table. For a function, we have looked at him as a set of ordered paths. We have looked at a function as a graph. Let's take a pause. Let's say someone wants to convert all numbers from 1 through 100. From miles, so 1 mile, 2 miles, 3 miles, 4, 5, 6, all the way up to 100. Do you believe that this table representation is a good way to demonstrate that?
No.
No. Could writing it as a set of ordered paths, would it work? If I wrote it as a set of ordered paths, would that be nice to look at?
No.
No. So table, set of ordered paths works as long as your function has very few points. Graph, doable, we've seen lines and stuff. So graphs are a good way to visualize. But we can't manipulate graphs. That's where the last approach comes into play, which is an equation. So we call y to be a function of x. We use y and x because of the xy plane, x-axis, y-axis. The reason why we put the letter f, any thoughts? Function. So when we say f of x, we're saying function . So y would be equal to f of x. Could I come up with an expression for this example? The input here is miles. so I can call it X. The output is
Kilometers.
kilometers, so Y. Good. I can write it in terms of X and Y. The first approach, Y is equal to 1.66 multiplied by X. If you have your calculator, plug in 1, what do you get? 1.66 times 1 is 1.66. 1.66 times 2, 3.22. 1.66 times 3, 4.83, and so forth. So that is simply Y represented as a function of X. Sure, I can write it in a different way.
But the 1.66 is not constant.
It is a constant. Why do you think that it is not?
Because it changes. It goes to or like from 3.22, it goes up to 4.83.
It changes only if you change the value of X. So when it is 1 mile is equal to 1.66 kilometers. 2 miles would be 3.22, 2 times 1.66. So sure, I could write it this way, but once again, we write it as Y equals f of X because of the number thing. So is a function?
No,
Why not?
two lines, two local points.
It's going to touch 2 points. If I draw a vertical line test, excuse me, a vertical line, it is going to fail the vertical line test. So no. How about this one?
No,
Over there. So no. How about that one?
Yes.
Yes. How about that one?
no,
No. Before we even evaluate, what are the inputs to the function? Before that, what is the function? Oh, the inputs are, so the inputs are 3 and -3. Now, what is our function? G of X is equal to X squared minus X plus 1. And now we've got to come up with an output. So anytime you have an exponent, put it within parentheses. It is good practice so that you don't make mistakes. So 3 squared minus or 3, X is 3 plus 1. What is 3 squared? 9. Minus 3 plus 1, which is 7. Good. So when the input is 3, the output is 7. If I want to write this as an ordered pair, what is the ordered pair? 3, 7. X is equal to -3. So the reason why I suggested always great to have parentheses is because of the negative. I've seen students do this in the past. When they plug in that -3, they would write it as -3 squared and forget to get rid of the negative and write the answer as -9. So don't, make that mistake. You can avoid it if you write it within parentheses. What is minus 3 squared? 9. Negative times negative 3 is positive 3 plus 1. And what do we get? So what are the inputs here? 0 and 4. What is the function? The function is square root of 16 minus x. Yes. So f of 0 would be square root of 16 minus 0. We get square root of 16. What is the square root of 16? It's 4. Easier way to remember, use a calculator. Or, I mean, easier way to do it, use a calculator, but you should know this. Root and 2 will get cancelled, so you'll have 4. When you plug in 4, you have square root of 16 minus 4. What is 16 minus 4? 12. Good. You can leave it as this, or you can simplify further. Four times 3 is 12. What happens if 4 comes out of the root? It becomes
2.
2. We have seen this before. What does that mean? Absolute value. We're trying to find the absolute value of 2 minus x squared. Could our answer be negative?
No.
No, we're trying to evaluate an absolute value function. Our answer will never be negative. So h of 1 is 2 minus 1 squared. Absolute value of 2 minus 1, which is the absolute value of 1, you get 1. H of minus 2, 2 minus minus 2 squared. What is minus 2 squared? 4. 2 minus 4, minus 2, but don't forget the absolute value. Absolute value of minus 2 is plus 2. Good.